Hello and welcome back to Calculus 3. We have the second part of the 16.5, which is on spherical integrals. Spherical coordinates and then spherical integrals, which is the triple integration in spherical coordinates. So spherical integrals for short. This is another coordinate system that is built on top of polar. So yesterday we saw cylindrical, where we had the polar coordinates, which is r theta, and then we had the z added to it to give us cylindrical coordinates. Now we're going to work on spherical coordinates, and spherical coordinates add another angle. So for spherical coordinate system, we use rho, phi, theta. Now this rho and phi is actually r theta, and then, so rho and theta is r theta. Rho is, for whatever reason, I don't know why they switched the letter, but rho is equivalent to your r from before, theta is still theta, and now you have this new angle phi. So when you are thinking about these coordinates, x, y, and z, you will have some angle theta inside the xy plane. Then you would have this distance over here to be rho. And then over here, somewhere on top, there will be the angle phi with the z-axis, and this point here on top would be rho phi theta. Spherical coordinates work with two angles at the same time, plus the radius to get to a point. So what we have now is the way you get this point is you draw the radius along the x-axis, then you rotate that in the xy plane to some angle, and then you rotate another angle up or down, depending on what kind of phi you have. So let's say you have a point 3 pi over 4 pi over 6. Now we're going to try and graph this the best we can. The first order of business is to get 3 down the x-axis. So that's your rho equals to 3. Once you are there, you have to determine where is your angle pi over 6 for theta. So let's say, right, if this is pi over 2 all the way around, then pi over 6 should be this angle here. And then you would swing this 3 onto this. So now this is actually polar coordinates. This is your 3 comma pi over 6 that you know from polar coordinates, because that sits on xy plane. And then we are going to find the 45-degree angle between x and z, which is pi over 4. That's pi over 4. And we are going to stand this up to get there. And this point here is 3 pi over 4 pi over 6. Now I am going to use my arm one more time to show. So the first thing you do is you draw the radius 3 along x-axis. Then you swing that 30 degrees in the xy plane, because that is angle theta. and then you go 45 degrees up to go to... Now, 45 degrees, guys, is measured from the z-axis. It's not measured from xy plane. 45 degrees, now, I chose a bad number, pi over 4, so that's an issue. You have seen this type of measuring before when you dealt with bearings in pre-calculus, in trig course. In trig course, let's have a little trip to pre-calc. Pre-calc 2 trig. When you dealt with bearings, you had north, south, east, and west. And you said north 30 degrees east. North 30 degrees east was that way, because that over there was 30 degrees. So you were measuring angles off of the north or the south. So you had north 30 east or north 30 west or south 30 east, right? But you were measuring off of the y-axis, and then your angles were dropping down. So now you are having the same thing for spherical coordinates. You are measuring the angle off of the z-axis going down 30 degrees or 60 or 45 or whatever amount of degrees you need to do. Which is why over here you would measure off of the z-axis, you would measure pi over 4. Now I chose a terrible number because it's also pi over 4 if you measure from the below, because right, to get the 90 it's pi over 4, pi over 4. So you measure thetas the same way you measure theta in polar coordinates, because it is a theta for polar coordinate, and that is from the positive x-axis. And then you measure phi from the positive z-axis downwards. And rho is your good old r, which is... Now, this coordinate system is excellent for us to work with the shapes that will contain a sphere, a ball, called spherical coordinates, obviously. If you're thinking about shapes, sphere has the equation x squared plus y squared plus z squared is equal to, let's say, what's a good number squared? 25, all right? If you want to convert this one into the spherical coordinates, this is equivalent to rho equals 5. Look at the equation. It's a joke. So we don't have to go with all of the x squared, y squared, z squared, none of that stuff. All we do, we just say rho equals 5, and that represents the sphere, the ball, in the spherical coordinates. So clearly, this should greatly simplify integration. So integral in rectangular coordinates x, y, z for a sphere is something that you can just look at and cry. Look what you have, right? For the sphere that sits in the x, y, z with the equation up there. What do you have for volume? You have a triple integral, and let's say you do the z, dy, dx. Let's say you want to put this order. Your domain is a circle in xy plane, radius in this case 5, because we chose sphere to be 5 wide. So top z is the square root of 25 minus x squared minus y squared. Bottom z is negative square root of 25 minus x squared minus y squared. For the domain, right, because we are doing dx, that's negative 5 to 5, that's easy. but the inner one is negative square root of 25 minus x squared, and a square root of 25 minus x squared as a positive square root. That's the integral for a ball, for a sphere, in rectangular coordinates. Well, that's way too spicy, right? It's a lot of calculations to do in this integral, right? So is there a way to simplify this? And obviously, yes. Now, if you want to solve that particular integral there, you would have to actually integrate z and have those square roots, and then once you are down to just dy dx, convert everything into polar coordinates, and then good luck from there, right? But there is a much easier way. Nice one. There's a much easier way to deal with this if you are using the spherical integral, because the spherical integral takes all of these, right, in terms of a ball, and you're integrating a ball, so that should be the easiest integral to do, to integrate a ball, to get a volume of the sphere. So before we get there, let's write down the spherical integral. And then we'll deal with the rest. So we have our triple integral over the surface S, surface D, whatever, of f of x, y, z, dv. And that's going to be the triple integral of f. Now, we have to convert everything in here, and I'm just going to write this. The conversion formulas, I'll write them on the side later. So rho sine phi cosine theta, so that's converting x. Rho sine phi psi theta, rho cosine phi, and then rho squared sine phi d rho d phi d theta. D rho d phi d theta. Now, limits. Alpha and beta limits that are angles for theta. Now, I don't like that they're using A and B. I have to use A and B because book uses A and B. I would rather use gamma and delta or other two Greek letters because these are also angles for phi. And finally, we have functions g of phi and theta and h of phi and theta. Now, this looks really intimidating, I understand. But it is, as it usually goes, if you think about it a little bit, it makes sense. First off, conversion formulas. They are given in these parentheses. X equals rho sine phi cosine theta. Y equals rho sine phi sine theta. And z equals rho cosine phi. These are equations that you can derive looking at those triangles that I drew earlier. And they convert x, y, and z. So if you are to integrate triple integral of, let's say, xy squared, you will take all of this mess, plug for x, all of this mess, plug for y, and square it, work out the algebra, then add the string that you memorize for triple integrals for spherical, and then go from there. Now, obviously, we'll do the example. All right, now it's the time for me to prove the formula for volume of the sphere, which is something that you guys might have on Wednesday. Oh, by the way, for honors, you guys are getting the same final as everyone else. No extra problems on the final. So you will have extra 2 problems on exam 3. You had extra problems on A. You have extra lab. You have extra problem on the project. So the final exam is identical to everyone else. So this is one of the proofs that, if anyone ever wonders, right, how they come up with the formula. Well, that's not how they came up with the formula, but it just works. So we're going to take a look at the volume of the sphere. Volume of the sphere. Formula. This is the proof. So I have a sphere. With the radius capital R. So equation over here is x squared plus y squared plus z squared equals capital R squared. We also learned that this transfers into rho equals capital R in spherical coordinates. So now for the volume, I'm going to set up a triple spherical integral, and I will be integrating. So again, I'm looking for volume, so there will be no function here because I'm looking for volume. All I'm going to have is a string which you have to memorize, which is rho square sine phi d rho d phi d theta. So this is the string. You know how you memorized dz r dr d theta for cylindrical integrals? You memorized r dr d theta for polar integrals. Now you're memorizing rho square sine phi d rho d phi d theta as a string for spherical integration. Our job now is to figure out what are the limits that we need to place so that we can integrate a sphere.
It's always going to be in that order.
Always in this order, yes. That's it. So the only annoying integrals are actually rectangular ones where you can swap. And if you have numbers everywhere, then they're easy. You just swap them. But if they have functions, you have to draw the domain, rearrange, and then put new functions as limits and so on. Okay. So time to construct the ball, starting from the radius, and then to take a look at all of these. All right. There is one part of this integral of the limits that usually makes no sense, so I need a disk, which in this case is given by this clock. All right, so we start by first writing the rho, because that's easy, right? Rho is 0 to r. We picked r to be the arbitrary radius for this sphere. If you want a 5, just put 5 there, and that will be the volume. You will be able to calculate the volume of the sphere that has a radius of 5. But we're going to use capital R, so we are actually getting the formula for. This is the proof for the formula. All right, so now d theta. We said that's the polar coordinates. And if you have your xy plane, which would be xy plane will be a circle, you want the radius to go all the way around to create a disk for the sphere. So theta will have limits 0 to 2 pi to create the entire disk. So what you're getting is like this round clock. You're getting a disk, right, which is infinitely thin, and it sits on xy plane. Now, look at this. We are going to flip this disk once. Not the full rotation 2 pi, but only pi. You rotate this 180 degrees. The disk has 2 halves. One half, in this case the half closer to you, will swipe the upper part and create the upper hemisphere, the upper half of the ball, while the other half of the clock that is closer to me will create the bottom one, which is why the limits are 0 to pi in the middle. That's usually the part that confuses people. We would like that to be 2 pi. No, because see the half of the disk, right, the upper half of the disk, when I rotate, is going to create upper half of the ball, while the bottom one is creating the bottom half of the ball. So they created a full ball by rotating only halfway, right? Just pi. If I rotate the full circle like this, then you would flip twice through the ball, because the top part would create half of the ball on top, and then the bottom part again, but the bottom part already created the bottom part, and then the top one again. So it's double work. So the limits are 0 to 2 pi because you want to create a full disk. And when you create the full disk on the bottom, then you get to rotate that disk halfway through, and you will have this. And now all we need to do is to integrate. You have your first integral in terms of rho. Well, that's just going to be rho cubed over 3. Sine phi is just a constant, right? Because we are integrating in terms of rho. So now you just integrate all of these, and you will have it. So we have the inner integral to give us rho cubed over 3 from 0 to capital R. And then we still have sine phi, d theta. This will give us now double integral 2 pi and pi. It will give us r cubed over 3 sine phi, d theta. Now this r cubed over 3 is a constant. You can kick that outside because those are all numbers. Remember, r could be 5 if you want to. You kick that outside and you integrate sine phi, which will give you negative cosine phi, computed from 0 to pi. And you still have d theta to worry about. We have r cubed over 3. And we have negative cosine pi plus cosine of 0, right? Minus and minus give you plus. D theta. Oh, there's still integral 0 to 2 pi. Oops. This is r cubed over 3 integral 0 to 2 pi of 2 d theta. Because cosine of pi is negative 1, and the negative makes it a positive 1. Cosine of 0 is 1. 1 plus 1 is 2. So now you have 2r cubed over 3 integral of d theta from 0 to 2 pi, which will give you 2 pi, for the total of 4 pi over 3 r cubed, which is the volume for the sphere. So volume for the sphere is 4 pi over 3. You are used to lowercase r cubed, but we had the capital R because I'm not sure why spherical coordinates are allergic to lowercase r. Radius has been r forever, right? Except when you get here. It becomes a rho for some reason. So, there you go. Another one of those excellent conversation starters, you know, let's say Thanksgiving dinner, or just dinner in general, have friends over. You can bring that up. So by now, you should be used to having terrible equations if you are using coordinate system that it's not appropriate for a shape that you're looking at. we said that equation for a circle, x squared plus y squared equals to, let's say, 9. It's not a function, and it's far more complicated than just r equals to 3, which is in polar coordinates. The same with a sphere, right? We have this terrible equation here that has x squared and y squared and z squared. It's not a function. And then you compare it to its spherical equivalent, and it's a joke. What is the equation of the plane in spherical coordinates? Well, it better be something terrible, because spherical coordinates are not meant for a flat plane, right? Spherical coordinates are meant for spheres and round objects, right? Just like cylindrical coordinates are meant for round objects. So here are a few of these shapes where spherical coordinates make sense. And if it's not on this list, well, stay away from spherical coordinates. It should be common sense. So sphere, right? Sphere is going to be rho equals, now lowercase a. That's going to be a ball with a radius a. Cone is another easy one where your phi is equal to some phi 0. So to draw a cone, right, you just have this phi 0 angle. That's the only thing that matters. The rest of the cone, right? Vertical half plane also makes sense because you have, as a part of these coordinates, you also have the polar coordinates here. So the same half plane as before that you guys had when you measure, right, theta 0. Horizontal plane is given by rho equal a secant phi. And if the plane actually goes through that value a on z-axis. So plane goes through the a value on z-axis. So a secant phi. Cylinder. Rho is equal to a cosecant phi, and a would be the radius of the cylinder. And finally, the sphere that is centered at 0, 0, some value z. Sphere centered at 0, 0, a is given by rho equals 2a cosine phi. So that's the ball centered, right? And you have the radius a, which is also the height over here from the origin. So these are some shapes that you can deal with. And let's take a look at a few examples. So one of the easiest problem, obviously sphere is the easiest problem. The next one on the list would be this cone that has a flat top. And it's pi over 3 right there. So this is the only thing you need to know. You don't need to know anything else to find the volume. You just need to know what is the angle, phi, and you need to know the height of the cone. So what is the volume of this cone? Well, we set up a triple integral without the function, so we just put rho squared sine phi d rho d phi d theta. Remember, this is a string that doesn't change problem after problem after problem. You put the same piece in. That's for spherical coordinates. Now it's time for us to figure out what we have for functions here and numbers. Well, first off, this is a full round object. We're not looking for half of the cone or a slice of a cone. We want the whole cone, so 0 to 2 pi would be the limits for theta. Now phi is 0 along z-axis, and then pi over 3, so 0 to pi over 3 on phi, because that's the separation that you have, right? And then when this one goes around, it creates the cone. So you have the z-axis, it falls down pi over 3, and then you go 2 pi to create the cone around it. The only thing that I need to do is to cut off its top, because the rho, in this case, right, rho is supposed to go, it's a radius that starts at the origin and goes up. So if I just put 0 to a number, it's going to create a spherical rounded top. Okay? But it's a flat plane on top. And we learned that horizontal plane has equation a secant phi. And our a is 4. So this is 4 secant phi. Because, I'll write it in blood, horizontal plane. And horizontal plane, we had it here. Rho equals a secant phi. The rho cut with a flat plane. The next problem, and then problem 46. We'll do problem 46 next because it's cool. So this is our integral, and now over 3, and we compute that from 0 to 4 secant phi. Values, we have 4 cubed, that's 64 secant cubed phi divided by 3, minus 0, no one cares, times sine phi d phi d theta. So 64 over 3 can be kicked outside. We still have our double integrals because we need to put this in a form we can integrate. And now 64 over 3 is kicked out. Secant cubed is 1 over cosine cubed, so you have sine phi divided by cosine cube phi d theta. And this is great because it's in a form for u sub. U equal cosine phi, du equals negative sine phi. So I have to put these negative signs everywhere. I have negative 64 over 3 integral 0 to 2 pi. That's the d theta. We don't have to worry about that one. Now the inner integral changes its limits. Cosine of 0 is 1, and cosine of pi over 3 is 1/2 on top. And this is great. du over u cubed. This is great because the 1/2, which is a smaller number on top, will get us a negative value, which will erase the negative 64 minus sign. So negative 64 over 3, integral 0 to 2 pi, the u to the negative 2 divided by negative 2, calculated from 0, not 0 to 2 pi, 1 to 1/2. There we go. d theta. So now that's negative 64 over 3, integral 0 to 2 pi. When I plug in, what is this? This over here is negative 2, no, lies, negative 1 divided by 2u squared. That's what it is. Negative 64 over 3, 0 to 2 pi. And now this mess. What do I have? I have a quarter, that's a half, that's a negative 2. And then the other one is plus a half. d theta. Yep. So this is negative 3/2. So this works out to be. So the last problem we are going to work on spherical coordinates is the one that has, it's problem 46. And this one has flat on top. It's flat on top, but it has this scooped out bottom. So it has a flat top, and the flat top is at 2. This one over here is at 1. And the question is, what is the volume? So to set this up, we are going to have, again, triple integral. We are looking for volume, so no function inside. So rho squared sine phi d rho d phi d theta. Standard setup. And now we take a look at our theta. It's a full round object, so 0 to 2 pi, because we are going to go around. We could have had just a slice of this. You know, you take this round object and you just cut a slice, like, you know, on a cake, you cut a slice. On a round cake, you cut a slice out. But, and in that case, it will be maybe 0 to pi over 4, 0 to pi over 3, whatever slice you cut out. But since it's a full round object, we have 0 to 2 pi. The next one is, the next one to look at is going to be the easy one to look at is rho. I have a flat piece on top. Now we know that the flat horizontal plane, right, the flat piece on top is going to be a secant phi. A is at 2, so 2 secant phi is the top. And that's the easy part. The bottom is also easy because the bottom is the sphere, right? You see it's scooped in, right? It's scooped from the bottom. So you can actually create a sphere over there with a radius 1. So it's just rho equal 1 is the bottom. So that's the easy part. Oh, I never gave you the angle over here. The angle is pi over 4. That's given as well. That escaped me. So now the angle for phi at z-axis is 0, and going out to pi over 4. we can have a hole inside. You can have another angle. Maybe you can have a pi over 6 and pi over 4. In that case, the object would be hollow. And then this would be pi over 6 to pi over 4. Right? Because it will be hollow. It will be an angle. It's just a whole bunch of possibilities that you can have with this. This integral is exactly the same as the previous integral with different numbers, so I'm just going to do this. What does that mean? Yeah, just do it. Exactly. Just do it. When you go home, you sit and you integrate this for about 15 minutes. It's exactly the same steps as here, it's just different numbers. So you are going to get something around 64, anywhere between 2 pi and 200 pi, whatever. You're going to get something like that.
How much credit would I get on the question? Like, really, just do it on the test?
Well, there will be no credit because there is nothing to award the credit for.
You guys set up all that?
Oh, no, if you set up, at least 2 or 3 problems on Wednesday will say just set up.
Oh, all right, I'm good then.
Just set up. And then you will have 2 or 3 problems where you will grind through the entire. There will be a single triple integral to grind through in terms of calculation, and possibly 2 or 3 double integrals to grind through completely. And there will be at least 2 or 3 problems that will just say set up, do not solve. So that's the setup. There will be 1 or 2 problems that will have a picture like this, and you remember those skateboarding ramps we did for double integrals and so on. So there will be at least 2 problems that will have a picture. There will be 1 problem at least that is a conversion problem, where you draw the domain looking at the limits. And right, so we'll talk about that during the review. Obviously, your quizzes are going. So okay, this is it for spherical. After the break, we go with the next section, which is center of mass. So that's the next one.